Hi, this is Mike Lawless. I'm a senior principal scientist at Simulations Plus, and in this video, I'm going to discuss predicting pKa using ADMET Predictor. It's very important to have a good model to predict pKa because pKa is so important to many pharmacokinetic properties. Solubility and permeability are two examples that are affected highly by the ionization of the compound. This next slide is simply an outline of the training video. First, I'll briefly discuss the S+pka model. Next, I'll discuss the pKa columns in ADMET Predictor that are produced when you calculate ADMET properties. I'll go into detail on the microstate display and graphs. Then I'll discuss a section on effect of ionization on solubility. And then the final two sections, I'll talk about descriptors based on the pKa model and then output options that are available in the SDF format.
This slide shows the observed pKa versus the predicted pKa's for the ADMET Predictor pKa model. You can see that the training set is very large, 47,000 ionization points, and the test set is made up of about 23,000 points. The root mean square error is 0.472, which means that about 70% of the predictions will be within 0.472 of the observed value. This data set was created in several different chunks. So the original S+pka model was trained on about 11,000 compounds from the literature. Then around 2012-13, we received a data set or went into a collaboration with Bayer Pharmaceuticals, and they provided 16,000 compounds with measured pKa data. Then recently, a year or two ago, the pKa data set was further expanded with new data from industrial partners. Roche contributed about 19,000 compound values, experimental values. Genentech provided 2,400, and Bayer Crop Science provided 4,100. So the latest data set contains about 71,000 ionization constants, and this model was additionally introduced in ADMET Predictor version 11. First publication from the Bayer Pharmaceutical collaboration came out in 2015 in the Journal of Chemical Information and Modeling, and there's the reference for that. And then recently, Robert Franskevich et al. Published a follow-up article that included the more recent data from Bayer Crop Science, Genentech, and Roche.
Okay, so let's look at how we calculate pKa values in ADMET Predictor. Just got a simple aminoquinazolin here. I'm going to highlight the molecule. And then I want to show the options under the pKa prediction. So I hit the settings button, and then I'm going to go into the ADMET model or the ADMET tab. And we see show secondary microstates contributing to 1% to the pKa. So by default, anything below 1% we don't display in the microstates display. You can limit the pKa values to be or below 14 or whatever number you want to enter here. Skip compounds with more than X ionization groups is turned off. Typically, if we're doing a large database and predicting properties, we might turn that on, and then if the compound does have more than 12, it will be skipped, and you can come back and do those later to get the whole data set. But it takes, the more ionization groups, the longer it takes to compute, and I'll talk about that in a minute. By default, we ignore aliphatic OH groups, so these type of alcohols typically have high pKa's, so they don't contribute to pKa's at 7.4 and below. We also ignore aliphatic amides for the same reason. And then we also have a carbon protonation model, but again, we're just going to ignore those here. So we'll just take those defaults then, and I'll click on the ADMET button and then calculate the pKa's. And if you go into the PhysChem properties tab, you'll see you get these three columns: S plus acidic pKa's, S plus mixed pKa's, S plus basic pKa's. These columns contain all the pKa's of the compound. If you double click on any of those cells, it brings up the microstate display. You can also just highlight that row and then click on the pKa button here, and that will display the microstates. In the upper left-hand corner of the window, we see some information. There's no acidic atoms in this molecule, 3 basic atoms, and then it lists the NH and then the aromatic nitrogens in the quinazoline ring. Here they have the number and then the type group. If you want to see what the numbers are, you can turn on the radial button here. So you see that atom 5 is this NH group. Atom 9 is the nitrogen that's kind of right off the other phenyl ring. And then this nitrogen is related to this. So we can turn those off. And you'll see we have 3 basic groups. The number of ionization states is 2 to the n. So that would be 2 to the third. So there'd be 8 displayed there. And as you see here, we only have 6 of them displayed here. And that has to do with going back to this default setting. So let's change this and let's display all of them. So if we set this to 0 and then compute the models again, we'll click on pKa's. Now you see the 8. And so these are in less than 1%. These are the additional 2 microstates that are displayed. If we start at the lowest pH here, you'll see that all of the ionizable groups are protonated, an NH or a hydrogen attached to them. And then as we increase the pH going up this way, you'll see that a proton is removed. So in this case, this nitrogen is the least basic nitrogen, so it's removed first. And then going up to the +1 state, you'll see that this group comes off, or the hydrogen comes off this anilic type nitrogen here. And then as we go up in pH, we get the neutral pH. We can display the various curves. So this is the fraction ionized versus pH. This is for all the microstates. So it's going to list all of the 8 microstates that we have displayed here, and then draw a graph for its fraction ionized versus the pH. We can also double click on this plot and at a certain pH, and it will show what the fraction ionized is at that particular pH. So here we're down around 0, and you see that the most stable one, or the highest fraction, is the H plus 95.1. So that refers to this microstate right here. So just this singly nitrogen, the quinazoline ring, is protonated. Now getting back to the chart, this is for the microstates display, and then you can click on this button and you'll see the macrostate. So these are just the formal groups here. Again, we can double click on that. Now we're at closer to a pH of 1, but we also see that the neutral, the +1 state is the preferred state. Clicking another time, we get your average number of protons. This is what you'd see from a titration experiment. We can go to the next one, the average formal charge. And then this one shows the average single proton affinities. So these plots are made, and what you see with pKa is that the pKa of one atom affects the pKa of another atom. What we're trying to do here is deconvolute that and just show the ionization for a single functional group. So here we see 3 lines corresponding to the ionizable groups in this molecule. And then this red point here is what's known as the pK50. So this is the pH at which 50% of that particular group is ionized. And so if you want to try and relate specific functional groups to the pKa of the molecule, you can use these average protonation states to achieve them. And what we see by this plot here is that the nitrogen that's in the quinazoline ring, this particular nitrogen, has the highest pK50 and therefore would be protonated first in this particular molecule. This information is used to create plots of solubility or log D versus pH. So if we double click on the log D or log P column for this molecule, we would get a plot such as the one shown here. So this is the predicted log D across the y-axis, and this is the pH across the x-axis. We can label the pKa's of this molecule. So here is around 4 is the pKa for the nitrogen within the quinazoline ring. Similarly, if we click on the S plus SW button, we'll get a plot of the aqueous water solubility versus pH. And we can also put that on a log scale or show the pKa's. So this is saying that here's the pKa of this particular molecule. Now, note the other two pKa's were below 0, so they're not shown on this plot. And then the lower we get in pH, the more the solubility will shoot up, and then it's fairly high at even a pH of 1.0. From the previous plots, we saw that solubility is affected by ionization, or the pK of the compound. So let's look at how this would work in a simulation. So we would look at GastroPlus in this case. And this plot shows pH on the y-axis versus the compartments in the GI tract. And then over on this y-axis on the right-hand side, this is the transit time. So in the stomach, the pH is between 1 and 2, less than 1.5. So this is going to affect the ionization state of the molecule. And then as it starts to work its way down the GI tract, you see that the pH in the duodenum goes up to 6 and then continually increases until the ileum 3 and then reduces a little bit in the cecum. And the amount of time spent in each one of these compartments is plotted out here on the right. So you're at 10 or 15 minutes in the stomach, and then it increases a little bit as you work your way down the GI tract and then decreases. And then these last two compartments here is where the compound would spend a large amount of time in a 24-hour period before being excreted into the feces. So if we look at the pH profile for the compound I just saw, put this into GastroPlus. So here we're looking at a 100 milligram dose of this particular compound, and it's a simulated pK run. So we see that this red line here represents the amount dissolved. And again, remember that this is a 100 milligram dose. So when the compound gets into the stomach, it dissolves very quickly, but it doesn't fully dissolve because the solubility in the stomach at pH 1.3 is 0.46 milligrams per milliliter. And that's less than the concentration in the stomach. So the whole molecule is not dissolved. Then it starts to work its way down the GI tract, additional amount dissolves, and then you see after about 2 hours, it slowly dissolves. But the oral fraction absorbed is only 68% in this example, and that's because of the low solubility of the compound. Now let's take a look at the compound if we add a morpholin group in this position off the quinazoline ring. So here you see immediately that the pK is below 6.4. You get a +1 state on the molecule. So that automatically increases the amount of ionization at the higher pHs, and that would result in substantially higher solubility starting here at about 4 and going up very quickly for this molecule. Now, what we call the native solubility, this is the solubility of the saturated solution, is 0.007 milligrams per milliliter compared to this other molecule that was 0.001. So this is 7 times more soluble at each one of their native pHs. And if we take this second compound with the morpholin ring, run a simulation at a 100 milligram dose, you'll see that in the stomach, because this is ionized heavily, and that increases the solubility, the amount dissolved goes up to, let's say, 95 milligrams, which is 95% of it dissolved. But then When it gets into the jejunum and duodenum, the compound actually precipitates, and this is precipitating because because it's not as soluble at this particular pH, because this isn't ionized as heavily. Now let's look at a few of the descriptors that are based on the pKa model. So these descriptors can be used in different models within ADMET Predictor because ionization is so important. You go to the descriptors tab here and then scroll all the way to the right. You'll see the ionization descriptors. Mostly we use fraction anion, fraction cation, fraction unionized, and fraction Zwitter ion. And so these represent the fractions of these particular species at the pH that was run to compute the properties. So typically that's 7.4 here. So if we look at fraction cationic for these species, or for these molecules, you'll see that this first molecule doesn't have a large amount, whereas the second compound, since we have this protonatable amine here, is a little bit higher at 0.09, so about 10% shown here, and then the rest is unionized. Now, if we click on this icon again here, and let's calculate the ionization at a pH of 1.2, and also calculate these ionization descriptors at this pH. Now, the reason that this is an option is normally you would want the ionization descriptors such as F cation predicted at 7.4, and that's what was used to build the model. So we don't typically turn these on unless we want to see the fraction at this pH. So I'll go ahead and do calculate. And now if we look at the fraction cationic, you can see that it changed. And now we have almost most of the molecule at pH 1.2 is ionized. Similarly for the second molecule. And then the third molecule even has a portion of ionization at this low pH. Now, this last molecule, since we're below the pKa of the acidic group, the fraction anionic is not very high there. This final slide just describes a few of the command line options. So if you would run ADMET Predictor on the command line, you have different options for outputting compounds in an SD file. So the first option is for medicinal chemist. So this gives the chemical structure in the neutral form as the output record in SD, and then gives the predicted pK values from the model. Physical chemist would output, saves multiple records for each molecule, and saves the individual microstates at different pHs. For the cheminformatics, this is the chemical structure in the neutral form, and then gives what the charge state of the atom would be at a given pH. And then finally, for a computational chemist, it gives multiple records for molecule, and it's used to save the individual microstates dominant at a given pH. And you might want to use this for input to docking. So it'll predict, let's say, the states that are available at pH 7.4. And some of these states might be interesting or helpful when the molecule is docked in a protein site. If it becomes protonated, it might could potentially donate a hydrogen bond to the protein structure and kind of interact with the protein structure. This concludes the training video on the S+pka model in ADMET Predictor. I appreciate your time and have a good day. Bye-bye.